Students, hi, it's Mr. Bob. This is particle physics video part 3, subtopic 7.3. Before watching this video, you should have watched the previous 2 particle physics videos, and hopefully you have some focus notes set up in your journal. And then a suggestion is about 3 to 5 days after watching this video, there's a section of the Oxford textbook that you could look at and read for further sort of information. And always a good idea to go back, you look at your notes, fill in those left-hand questions, chunk or highlight parts of it, and identify points of confusion. Always avoid mindless copying, stop the video and rewind if necessary, selectively write down things, don't write down everything. And if there's a sample problem, try and pause the video and have your brain think about it. And again, if you're confused, points of confusion and seeking out resources is a really good idea. 3 essential questions. One is, what is quark confinement? The second is, how is a Feynman diagram useful? And the third is, what is the Higgs boson and why was its discovery so important? So quark confinement, interesting thing. So remember, quarks are those constituents that make up things like baryons and mesons. And quark confinement is basically saying this. We have tried in a lab, in a science lab, to basically separate a single quark from the other quark. So for example, if it's a baryon, as you can see here, we've tried to basically separate a single quark from the other 2 quarks in there. And the way you do that in a lab is you add energy to that basically that baryon in an effort to kind of separate it as you would anything, right? If you want to separate protons and neutrons from a nucleus, we know you have to give energy to the nucleus to basically be able to separate them. That's what that binding energy is all about. So here's what's happened. We've provided more energy to get them to move apart. Let me show you here in this next slide. Here we are. Here's the quarks. By the way, that's exactly what quarks look like. Just kidding. This is a meson, right? And so add energy, keep adding energy. All of a sudden, in a blink of an eye, less than a blink of an eye, we get another meson, another complete meson. And so what happens is we add so much energy, we have to add so much energy to it that in essence, 2 additional quarks come into existence all of a sudden. We get a quark-antiquark pair, and basically that energy that we have had to put into the system has been so great that you get the production of 2 more quarks. And once again, we're in the same predicament. We have not isolated a quark by itself. So that's what quark confinement is, and it's something you should be aware of. Let's move on to something called Feynman diagrams. Okay, now this is a very complex topic, and we're just going to scratch the surface of it here in IB Physics. The math involved with this is graduate level and beyond math. It's a topic that just obviously requires a lot of specialization, but it is still instructive for us to just get a touch or a taste of what it is about. So Richard Feynman, famous scientist, developed this sort of pictorial representation of what's happening when particles come close to each other and interact with each other. And he basically created these diagrams, and in one set of axes there's space, and another set of axes is time. We're going to see how this works here in a moment. Just an FYI, sometimes you'll see in certain resources that time is on the vertical axis and space is on the x-axis. If you ever see exam questions from me, I'll always represent it this way. I have seen IB exam questions where they've reversed the 2. Okay, so let's take 2 electrons approaching each other, one from the top of the page up there and one from the bottom of the page. And we know from classical physics perspective, we know as they approach each other, what happens? They repel, right? Well, a purely spatial sketch would look something like this. But notice as they get closer, there's what we call this bubble of ignorance. So what is exactly happening to cause them to repel? We don't have a good pictorial representation of it in this way. With the Feynman diagram, we can basically get a little more specific and understand a little more detail what's happening here. And remember, with the standard model, what we believe is happening with these forces is that particles, those boson particles, are being exchanged. In this case, the boson that's being exchanged is a photon, right? And so we'll show it here more carefully, but notice this is what the Feynman diagram is kind of showing. With time on the x-axis, you can actually kind of spread out this reaction and show a little bit more about what's going on. So notice you have the ingoing and outgoing particles are labeled. And let's go to the next slide because you can even see it better here. The particles represented by straight arrows. And then the exchange force particles, remember the bosons, are represented by either wavy lines, right? If they're electromagnetic or if they're a weak exchange, they are represented by wavy lines. And then if it's a strong exchange, and meaning involving a gluon, you have those curly Qs. And by the way, this is exactly how it's supposed to be. I'm not making this up. So this is drawing at its best. So here's the full sample problem one, which is showing the repulsion of two electrons, which looks something like this. The two electrons coming in, get close enough to each other, they exchange that photon, and they move out. Looks something like that. And you show the exchange particle, the photon, represented there. You label it. Another sample problem, and try this one on your own before you continue the video. Try to draw the diagram for one electron emitting a photon. Well, that would look something like this. You have the electron coming in, photon is emitted, and the electron continues along its way. Here's a third and fourth sample problem we can look at with Feynman diagrams. Let's say we have a photon that produces an electron-positron pair. This is what was talked about in the podcast about what's the antimatter, right? If you get a high enough energy level, like in the X-ray range photon, you can have enough energy to produce an electron-positron pair. So that would look like this. Photons coming in, and all of a sudden, electron and the positron are there. And then the fourth sample problem, the reverse, basically. Let's say an electron and positron come together, and we know from the podcast that they annihilate each other, right? And so that might look something like this. Electron and positron come in, they annihilate each other, and all you get coming out of that reaction is a photon, a high energy wave. You may have noticed something curious about these two diagrams. Notice the positron, the arrow here, okay? And in fact, with Feynman diagrams, antiparticles arrows are drawn as if they are going back in time. Now, they are not actually going back in time, but I'm just going to say at this point that there's some really complex math that even I do not understand, and I've tried to make an effort to understand why this is. I've searched the web, read some websites. This next slide, I'm just going to show you this. Why do antiparticles point backwards in the Feynman diagram? I'm just going to share this text with you. I'm not going to read through it. I'm not going to pause. You can pause the video and kind of read through it. It is complicated. You just need to know that whenever you have an antiparticle in a Feynman diagram, the arrow needs to point back in time. Again, pause this video if you want to read that in its entirety and investigate it. Okay, a quick joke. Have you heard about the reclusive baryon that doesn't really interact much with others? They say it's a bit quirky. All right, last topic is the Higgs boson. And here's a quick brief history to start us out. In the 1960s, in quantum physics, there was a lot of theoretical and experimental evidence to support quantum physics, okay? But there were still some inconsistencies. For example, one of the things that quantum physics predicted, the equations predicted, is that electrons should be massless, but we know they're not massless. So how could they reconcile this? Well, three physicists got together and tried to tackle this, and they proposed some math equations that accounted for this understanding, as well as suggested that there must be a field that exists throughout all of space. In other words, they proposed a modification that would account for everything we already knew and didn't disrupt that, but then also added this new wrinkle. So what they proposed is that there was this field, and that to the extent with which particles interacted with this field, that gave them a certain amount of mass. And so in this case, what we have is what's called the Higgs mechanism. So the Higgs mechanism suggests that particles by themselves do not inherently have mass. It's only through their interaction with the Higgs field where they gain a certain amount of mass, okay? So all through space is imbued with this Higgs field. And just like the electromagnetic field has a particle associated with it, so does the Higgs field, okay? In this case, the Higgs field, there's something called the Higgs boson. And so what you can say is the Higgs boson is an excitation of the Higgs field that is predicted by the standard model. Here is a video, a 3-minute video that shows you a really good analogy of how the Higgs field works. Let's watch. It's by Don Lincoln from Fermilab.
If this sounds confusing to you, you're not alone.
Start over.
Without a doubt, the most exciting scientific observation of 2012 was the discovery of a new particle at the CERN laboratory that could be the Higgs boson, a particle named after physicist Peter Higgs. The Higgs field is thought to give mass to fundamental subatomic particles like the quarks and leptons that make up ordinary matter. The Higgs bosons are wiggles in the field, like the bump you see when you twitch a rope. But how does this field give mass to particles? If this sounds confusing to you, you're not alone. In 1993, the British science minister challenged physicists to invent a simple way to understand all this Higgs stuff. The prize was a bottle of quality champagne. The winning explanation went something like this. Suppose there is a large cocktail party at the CERN laboratory filled with particle physics researchers. This crowd of physicists represents the Higgs field. If a tax collector entered the party, nobody would want to talk to them, and they could very easily cross the room to get to the bar. The tax collector wouldn't interact with the crowd in much the same way that some particles don't interact with the Higgs field. The particles that don't interact, like photons for example, are called massless. Now suppose that Peter Higgs entered the same room, perhaps in search of a pint. In this case, the physicist will immediately crowd around Higgs to discuss with him their efforts to measure the properties of his namesake boson. Because he interacts strongly with the crowd, Higgs will move slowly across the room. Continuing our analogy, Higgs has become a massive particle through his interactions with the field. So, if that's the Higgs field, how does the Higgs boson fit into all of this? Let's pretend our crowd of partygoers is uniformly spread across the room. Now suppose someone pops their head in the door to report a rumor of a discovery at some distant rival laboratory. People near the door will hear the rumor, but people far away won't, so they'll move closer to the door to ask. This will create a clump in the crowd. As people have heard the rumor, they will return to their original positions to discuss its implications, but people further away will then ask what's going on. The result will be a clump in the crowd that moves across the room. This clump is analogous to the Higgs boson. It is important to remember that it is not that massive particles interact more with the Higgs field. In our analogy of the party, all particles are equal until they enter the room. Both Peter Higgs and the tax collector have zero mass. It is the interaction with the crowd that causes them to gain mass. I'll say that again. Mass comes from interactions with the field. So let's recap. A particle gets more or less mass depending on how it interacts with the field, just like different people will move through the crowd at different speeds depending on their popularity. And the Higgs boson is just a clump in the field, like a rumor crossing the room. Of course, this analogy is just that, an analogy, but it's the best analogy anyone has come up with so far. So that's it. That's what the Higgs field and Higgs boson is all about. Continuing research will tell us if we found it, and the reward will probably be more than just a bottle of champagne.
All right. So just to kind of recap what they said in that video, the room full of physicists was the Higgs field, okay? And so suddenly a famous person enters the room and tries to cross the room. Those physicists, this says Einstein, but it could be Peter Higgs, that person's going to have a hard time crossing the room because the physicists are going to cluster around them. So that is a particle that's interacting heavily with the Higgs field, and therefore it has a high mass. But if I enter the room, I mean, I know I'm a popular guy, but I'm not really popular with particle physicists. Nobody's really going to want to interact with me. So I pass with the physicists relatively unimpeded. There's no effective mass for me because I can walk through the room easily. So I am a low mass or massless particle. And then the final idea is that if someone whispers a rumor, then there's a kind of clumping in the field, and that clump kind of propagates as more people come closer, listen to the rumor, and then go back to their position. So that's the Higgs boson. All right. So, and this was kind of brought up by Burton de Wilde. So, and this is a picture of the Large Hadron Collider. By the way, in July 2012, Large Hadron Collider project team confirmed the existence of the Higgs boson. And there's a fascinating documentary called Particle Fever that I hope you all get a chance to watch. We might be able to reserve some time to watch it, or at least part of it, as part of this course. Okay. So to finish off today, I have a little music video for you that was produced by scientists at the Large Hadron Collider. So go ahead and watch and enjoy.
Oh yeah. I'm about to drop some particle physics in the club. gravity is super duper fly. You know what I'm saying. Check it.
27 kilometers of tunnel underground, designed with mind to send protons around. A circle that crosses through Switzerland and France. 60 nations contribute to scientific advance. Two beams of protons swing round through the ring they ride, till in the hearts of the detectors their mates collide, and all that energy packed in such a tiny bit of room becomes mass particles created from the vacuum. And then
Oh yeah.
LHCb sees where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head. We see asteroids and planets, stars galore. We know a black hole resides at each galaxy's core. But even all that matter cannot explain what holds all these stars together. Something else remains. The star matter interacts only through gravity. And how do you catch a particle? There's no way to see. Take it back to conservation of energy, and the particles appear clear as can be. You see particles flying in jets they spray, but you notice there ain't nothing going the other way. You say my law has just been violated. That don't make sense. There's gotta be another particle to make this balance, and it might be dark matter. And for the first time, we catch a glimpse of what must fill most of the known verse, because LHCb sees where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. Antimatter is sort of like matter's evil twin, because except for charge and hiddenness of spin, they're the same for a particle and its anti-self. But you can store an antiparticle on a new shelf, because when it meets its normal twin, they both annihilate. Matter turns to energy and then it dissipates. When matter is created from energy, which is exactly what they'll do in the LHC, you get matter and antimatter in equal parts. And they try to take this back to when the universe starts, the Big Bang, back when all the matter exploded. But the amount of antimatter was somehow eroded, because when we look around we see that matter abounds, but the antimatter's nowhere to be found. That's why LHCb sees where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head. The Higgs boson, that's the one that everybody talks about, and it's the one sure thing that this machine will sort out. If the Higgs exists, they ought to see it right away. And if it doesn't, the scientists will finally say there is no Higgs. We need new physics to account for why things have mass. Something in our standard model went awry. But the Higgs, I still haven't said just what it does. They suppose the particles are mass because there is this Higgs field that extends to all space, and some particles slow down while other particles race straight through like the photon. It has no mass, but something heavy like the Quark extravagance. And the Higgs is the boson that carries the force. It makes particles take orders from the field that is its source. They'll detect it. When LHCb sees where the antimatter's gone, Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The same you might think that gravity is strong, 'cause when you fall off your bicycle, it don't take long until you hit the earth and you say, dang, that hurt. But if you think the force is powerful, you're wrong. You see, gravity is weaker than weak, and the reason why is something many scientists seek. They think about dimensions. We live in just three, but maybe there are others that are too small to see. It's into these dimensions that gravity extends, which makes it seem weaker here on our end. And these dimensions are rolled up, curled so tight